Chapter 7, Section 6, Cofactor Expansion. Cofactor expansion, also known as Laplace expansion, is a systematic method to calculate the determinant of a square matrix by expanding along a chosen row or column. It reduces the calculation of the determinant of an n by n matrix into a smaller determinants of n-1 by n-1 matrices. As the general formula, cofactor expansion can be expressed in this way. For an n by n matrix A, the determinant can be calculated by expanding along any row I or column J. This formula is complex, so in the following, let's see the concrete operation. For simplicity, let's see a case of a 3 by 3 matrix. First, expand the first row. Next, calculate the minors. Each minor is the determinant of a 2 by 2 matrix. Then, substitute them back. This yields the determinant. The term -1 to the power of I plus k is sign alternation. This factor ensures the correct sign is applied to each cofactor. The sign alternate is a checkerboard pattern for any matrix. Some of you might want to ask, does calculating the determinant require repeating for all rows? No, it does not. When using a cofactor expansion for a determinant, it is sufficient to expand along only one row to calculate the determinant. For example, in a 3 by 3 matrix, you can expand along the first row without needing to repeat for other rows or columns. Let's focus on the general formula of cofactor expansion. The sigma notation indicates that we are summing across the columns of a specific row for expansion. For example, if expanding along the first row, this summation iterates over all columns in the first row. If you choose to expand along the first row, the row index I is fixed to 1. This means that to calculate the determinant, we only need the elements of the chosen row, their corresponding minors, and the sign factor. So, why is it unnecessary to repeat for other rows or columns? The determinant of a matrix is invariant under which row or column we use for expansion. In other words, regardless of the row or column chosen, the calculated determinant will always be the same. For example, by expanding along the first row, we calculate the determinant as expressed in this way. If you instead expand along the second row, the result will still be the same, even though the terms involved will differ. Thus, it is sufficient to calculate the determinant using only one row or column. In this context, the sigma notation sums the contributions of all elements in the chosen row or column. Specifically, each element is multiplied by its corresponding minor determinant, and each term is adjusted by the sign factor. The final determinant is the sum of these sign contributions. By choosing only one row or column, you completely determine the value of the determinant. To calculate a determinant, you only need to expand along one row or column. There is no need to repeat the process for other rows or columns, as doing so would be redundant. However, for computational efficiency, it is often best to choose a row or column with the most zeros, as this minimizes the number of calculations required. Thank you for watching. Please thumbs up and subscribe to my channel.